another session, that's session 2 under unit 1, evidences for non-triene-like nature of benzene. So in the session 1, we talked about the fact that the structure proposed by Kekule wasn't the actual structure of benzene. So in this unit, in this session, we'll be looking at the evidences that were used to back this fact. At the end of the session, you should be able to explain the thermochemical evidence for non-triene-like nature of benzene, explain the high stability associated with benzene, and of course, state all the evidences for non-triene-like nature of benzene. So the first evidence we'll be looking at will be the thermochemical evidences, which basically talks about hydrogenation of an alkene. So, as proposed through this thermochemical evidence, what it tells us is the fact that if you have one alkene functional group, which is a double bond, and you hydrogenate it, the amount of energy that is being released is 28.6 kilocal per mole. So, one giving us this amount, we would expect two double bonds to give us or release an amount of energy of 57.2 kilocal per mole. Then we will actually expect 3 of this to produce times 3 of 28.3, which is what, 58.8 kilocal per mole. But in real sense, that is not the case for benzene. So what it tells us is that benzene producing 48.8 kilocal per mole energy tells us that the 3 double bonds we see in the benzene ring are not the same as the double bonds we see in the 135 cyclohexatriene structure of Kekule. So it further proves that the double bonds we see in benzene are not the same as the double bonds we see in cyclohexatriene. And this next slide further. So this next slide further confirms the fact that 1 will produce this amount of energy, 2 will produce times 2 of this energy, and 3 will produce times 3, 85.3 kilocal per mole. That's 3 double bonds. However, the actual benzene itself has far less energy as compared to that of cyclohexatriene. So this further confirms the structure of benzene to be different from the structure proposed by Kekule. The next evidence we'll be looking at is the chemical evidences. Now, chemical reactivity of benzene and then that of Kekule as proposed by Kekule, which is the cyclohexatriene, suggests that the Kekule structure behaves exclusively as an alkene. What it means is the kind of reactions alkenes undergo are not the same as the kind of reaction benzene also undergoes, even though they seem to have the same similar structure. Chemically, they are completely different. So cyclohexene undergoes, which is an alkene, undergoes an addition reaction, whilst benzene undergoes a substitution reaction. What it means is in cyclohexene, that is the alkene functional group having this, the bromine molecule actually attacks the double bond and adds up to the ring. So as you see, this product comprises the 2 bromine functional groups, the 2 bromine groups. Well, when you come to our benzene ring, that is completely not the case. There's a complete difference in the chemical reaction of these 2 compounds. Now, benzene actually undergoes substitution reaction, where it replaces some of its substituents to allow other substituents to come in. So this bromine actually substitutes the hydrogen in the benzene ring, and then the hydrogen in the benzene ring that has been substituted reacts with another bromine group to form hydrogen bromide. Two complete different structures are formed in the chemical reaction involving these 2 compounds. So this further proves that the 2 structures as proposed by Kekule is not the same as the actual structure of benzene. Now, the last evidence is the molecular orbital theory. It's based on the molecular orbital theory. It talks about bonding in benzene. Now, each carbon atom in benzene is sp2 hybridized. Therefore, benzene is a planar molecule with bond angle of 120 degrees. And also, The adjacent p orbitals of each carbon in the benzene ring overlaps to form a pi cloud of delocalized pi electrons above this plane and then also below this plane, forcing the structure to assume a planar shape. And this is not the case in 1,3,5 cyclohexatriene.